Yeah.
Yeah, so hi everyone. So welcome to Dianzhao Lee's talk. He has finished his or finishing his wrapping up his PhD now in TU Dresden, and he'll talk to us about RL for autonomous driving. So I take it away, Dianzhao.
Yeah. And thank you, Professor Mangaram. And I thank you all for inviting me to present my work here at xLAB. My name is Dianzhao Li. I'm currently a PhD candidate at TU Dresden. So my topic of this presentation is reinforced learning for autonomous driving, human-informed, ethical, and transferable agent. So before I start the presentations, I would like to have a short introduction of myself. I'm currently working my PhD in traffic engineering at here TU Dresden under the supervision of Professor Osip O'Quinn from TU Dresden and Professor Liam Paul from University of Montreal and Dr. Martin Taiber from TU Dresden also. So my research is mainly in the intersection of reinforced learning based autonomous system with path planning and application to the cyber physical systems. So let me move to the next. So here is the overview of my talk. First, I will start with the motivation, then follows the background and related works, which setting the stage for three main contributions of my work. First is human-informed learning. Second is ethical and safe RL. And third is sim-to-real transfer. Then finally, I will wrap up with the discussion, limitations, and possible future works. So why we discuss the autonomous driving dilemma here? And we all know that from 2024 to 2025, there is a turning point. We know that there is some incident happens during the last years, and there is a crew strikes a pedestrian for 20 feet in US, and there is also Tesla FSD record, which involved almost 300,000 vehicles. And this incident underlies that very critical challenges. So why the autonomous vehicles making mistakes that the humans are consider ethical unacceptable, right? And there is a survey from AAA that only 30% of the people, of the humans, trust the autonomous driving vehicles. And this is a very critical challenge for us. And despite all the progress we have made for autonomous driving systems, and this challenge not only focus on the technical part, but also for the social part. And this is why I would like to work on this topic. And as we discussed, the challenge for autonomous driving is the autonomous vehicles must to coexist within a very mixed traffic scenarios. It need to interact with the human drivers. It need to interact with the pedestrians and the cyclists. And it need to make high-stake decisions, which requires safety, efficiency, and ethical considerations. And before and after we train the simulated agent in the simulations, we need to consider the sim-to-real gap when we deploy the agent into the real world. And yeah, all these challenges raise me a very interesting research questions. So how can we design intelligent systems that behave more responsible and harmoniously in a human-machine interaction scenarios that also able to generalize to the real-world scenarios in a more transparent way? Now let's position us in a more broader autonomous vehicle scenarios. So we all know that the autonomous vehicle has two pipelines normally. So we have the modular systems, we have the perceptions, and we have the prediction, planning, and control. And for each of these models, we have the traditional method and with the also with the machine learning method. And all this method can be used for each of these modules. For example, we have edge detections, common features, particle features for the perceptions and the localizations. And then we have the A star for plannings and the PID and MPC for controls. And we have also the machine learning based method. We can use CNN for perceptions. We can use RNN transformer for predictions. And we can use imitation learning or reinforced learning for plannings and controls. And the second pipeline here is end-to-end. It directly maps the sensor input to the control output. And we can use imitation learning and reinforced learning to train the agent in the simulations or with the real world data. And this sets the stage and why I would like to use reinforced learning to train the agent in the simulation. And because reinforced learning handles the sequential decision makings under uncertainty, which is exactly driving in the real world looks like. The reinforcement agent learns a policy that's in a simulation with trial and errors, and it is easy to adapt to a dynamic environment. Unlike the imitation learning, so imitation learning basically it just mimic from the real world data, and it cannot learn from the edge cases, which is not it's not possible, but it's very dangerous to collect in the real world. Therefore, we can use reinforced learning to learn the edge cases, which is risky scenarios, and to let the agent to handle these very long tail scenarios. However, there is still some limitations for reinforced learning. The sample efficiency, which is a very big drawback for reinforced learning, and compared to the imitation learning. And we also need to design the reward function for the reinforced learning agent. And the sim-to-real gap also hindered the deployment from the simulation to the real world. And we also need to consider the safeties when we deploy the agent into the real world. So all this motivate me to focus on this research topic, which is deep reinforcement learning for autonomous driving, human-informed, ethical, and transferable agent. There is three parts of contribution here. First part is the human-informed learning and ethical reasoning and the sim-to-real transfer. We will discuss each of these contributions in the later slides. And before we dive more into the contributions, let's have a small recap. What is reinforced learning? Reinforced learning basically, one agent just learn in the simulation by trial and errors, try to optimize its policy. So that position, it can be assumed as a Markov decision process. And we can position us in a driving scenarios. For example, if we drive on the road, we observe there is one vehicle driving in front of us. So this is our current state. Then we need to decide, okay, what should we do? We to make a left turn, or we make a right turn, or we just keep within the lanes. So then according to our current states, we decide, okay, we just make a left turn to overtake this vehicle. And meanwhile, we will receive a reward according to the action we took and the states we are currently on. And there is also a so-called discount factors, which measures how far your agent prefer the future reward. And the objectives for reinforced learning is to find an optimal policy that can maximize the expected discounted cumulative reward in the future. Okay, this is the reinforced learning. And next, we move to the first contributions of mine, which is human-informed learning. We all know that the autonomous vehicles will need to interact with the human drivers in the next few decades, right? And therefore, we need the autonomous vehicle to harmoniously interact with the human players, human drivers. And it also needs to improve the safety, comfort, and efficiency. And here for this work, we consider a very simple scenarios, which is car following. And car following basically is there is a vehicle driving in front of us, and we need to follow this vehicle while keep a desirable distance and also maintain the driving efficiency. And for this, we propose a framework that we want to mix the real-world datasets and with the generated datasets in the simulation by reinforcement learning. And it consists of two stages. First stage is we learn directly just from the simulation. And here the repeat buffer basically is how the agent store the past experience and to update its policy for a policy agent. It's a trick to improve the sample efficiency. And the second stage is we learn, we just change or mix the real world datasets and with the simulated datasets into the repeat buffer, let the agent to learn either from the simulated behavior or from the real-world human drivers. We want our agent to have the best behavior, not only from the human drivers, but also from the designed reward function. And after we trained, and we want to evaluate, and we use a so-called Napoli dataset. The Napoli dataset is collected in Napoli, Italian, and it was a car following dataset, and it was constructed with 5 vehicles following each other. And it covers very diverse driving scenarios, including urban drivings and highways, and also some country road drivings. So this is basically the results. And we show first figure is the velocity of our proposed agent and with some baselines. And second figure is the bumper to bumper gap between the ego vehicles to the leading vehicle. And for comparisons, we have some baselines. We have a behavior cloning baselines, and we have a fully off policy agent. The behavior cloning agent just basically it's just we train networks that purely learn from the real world human data. And this fully off policy agent also learn from the real world datasets, but with reinforcement learning style. And we can see from the first figure that these two baselines fails at the very beginning of the evaluations. And this indicates that true agent is not suitable for this kind of reward scenarios. And we also have this pure RL agent, which we purely trained without any real world datasets. And this agent shows a more passive driving style. And this we can see from the second figure and indicate as red color, yellow color. And at the high speed stage, which is from 0 seconds to maybe 75 seconds. And this agent tends to have a larger distance to the leading vehicle. And however, when the leading vehicle just stops or decreasing, um, this per RL agent tends to have a closer distance to the agent, which is undesirable. And this is because we design the reward function and the agent just purely learn from the reward function. And this reward function at the most of time can be suboptimal. Then we have the intelligent driver models, IDM, which is a rule-based car following model, marked as green. And we can see that this model shows is too aggressive and keeps a closer distance to the leading vehicle all the time, either in the high speed or in the low speed. In contrast, our two-stage and proposed agent is able to show a more mature driving policy.
So just a
That's
question on this
yeah,
mature driving policy. You
yeah.
desire that you be like the yellow curve on the right hand side?
Yeah.
That at higher velocities you have further distance.
You mean
What is your goal is to have modulate the bumper to bumper gap based on the velocity, right?
um yeah, we want to because the bumper to bumper gap defined bumper to bumper defined our ego vehicle the distance to our ego vehicle to the other vehicles. And in the high speed, we should keep a suitable distance to the leading vehicle because we want not only want to have the safety concern, we also want to have the travel efficiencies. So we don't want to keep a very large distance to the leading vehicles. We want to have a suitable distance.
So what
And
is
in
suitable in this chart over here? Like on the right hand side, if you could show suitable, is it between 15 to 20 for
yeah,
time 0 to 75, or like is there a band and the band is moving based on the velocity, or
um, for this at the suitable distance for this velocity, according to one of my colleagues, it could be from 12 meters to 20 meters. So for this high speed, which is range from 10 meter per second to 50 meter per second when you drive, when you do the car following. And
okay.
yeah,
So I think the distance should be speed dependent.
Yeah, yeah,
Maybe
yeah, yeah.
something like time headway. Yeah.
Yeah, yeah.
Like
But doesn't the ACC adaptive cruise control, like it has a two current PID, two like a hierarchy of PID controllers, and one is maintaining this heading distance that is, speed aware, right?
yeah, I think they use the PID to control, but um, I think the ACC just want to keep the speed at the constant or just keep within the lines to the line keeping. And here we also need to consider the interaction with other with the leading vehicles with other vehicles.
Okay, okay. Yeah, yeah. I think what I'm missing here is like a specification of what you want, because you're showing all these
Ah,
trajectories here, but what is like the desired operating range? But I guess you're saying that's between 12 to 20 for the first part. But that's like is there like a systematic way of like based on like the stopping distance, stopping time, like that, right? So
yeah, actually, we will discuss this maybe in the next slides. There is also
okay,
some
okay.
performance metrics, and we can use to evaluate
Sure.
how what's the desired behavior.
I do have one question.
Okay,
Yeah.
some more
So a
questions,
quick
but
question.
Yeah.
So I'm wondering if you're missing a baseline here, which is that you
yeah.
have this human data set. How about you do like inverse reinforcement learning to distill a reward function from
Ah,
that, and then train
yeah, this
based
is
on
the
both of them?
yeah, this is a very good questions. And I did this work at 2023, and we didn't dive into the inverse RL yet, but now we are kind of working on this. And yeah, this is already some past works. And yeah, this is a very good questions, and we can just dive into the inverse RL to have some reward function extracted from the data sets, of course.
Yeah, that's great. And I guess my other quick follow-up question is that I'm just this is from my own experience working with this type of, augmenting RL with not even human data, just some other data. Because
Yeah.
one thing I experienced personally is the catastrophic forgetting. Because what's happening here is that you first train your RL policy and then you modify your replay buffer with some other data, which is not trained under the previous policy or whatsoever. And my personal experience is that it can cause some catastrophic forgetting if your reward is mismatched with the data. Have you experienced that?
Yes, we have. And we use prioritized external replay to handle this somehow. And we also construct the data sets, the real world data. And we construct this data and we use the reward, we have the reward function defined, right? And then we compute the reward for this, also for this reward assets. And then we also fit not only for the actions, and we fit the reward. This kind of solve the problems. But however, we also want to, and we also use KL divert losses to constrain the policy not to get fall far away from the old policy. And yeah, this kind
Thanks.
of solve the problems.
Yeah, kind of the follow-up to that, because your two stage, your first stage is I saw it's DDPG on the data set, right?
Yeah.
So that would be purely offline or off policy training. And then on the second stage, you're training in the simulator. I guess the question is, do you also collect data sets so that it's also off policy?
No, and the first stage is we train it in the simulation. It's yeah, it's off policy. In the second stage, we mix the simulated data with real world data. And your question is, can you repeat your question again? Sorry, I didn't.
It's more like in the second stage, do you keep it off policy or is it
Yeah,
changed to
the
something that's
second
on
stage is
policy?
still off policy. Yes.
Right. And then in the simulation, which how is the data generated? Is it through the policy that you train in the first stage?
Yes. At the beginning, of course, the off policy. You always update the policy. At the beginning, we update the policy with old. We update the policy according to all the data, and then we mix the new data, and we gradually feed the data into the repeat buffer with ratios, and then we gradually update the policy. I don't
No,
know
I
if this.
mean the data that you generated in the simulator.
Yeah.
What is controlling the card that generates the simulation data?
It's current policy. You
Oh, the
mean?
current policy.
Yeah, it's
Okay.
current policy.
Okay. Thank you.
So may I have a very high level question? So what does it really mean by human informed learning? Yeah.
Human informed learning is we learn from the human data,
Mhm.
and we want our agents just not learn from the human data and outperform the human driving behaviors. So we want our agents be more suitable for human machine interaction scenarios. So not only for just maybe better than the human drivers contains in the real world data sets.
Okay, so how can you capture, like how can you quantify the level of human and CV and autonomous vehicles interactions?
You mean the performance metrics we have? How to
Not
qualify?
not only the performance metric, but also the how can you quantify that the policies uh like how good it is in terms of human and AV interactions.
And for this, we use some performance metrics, and we use maybe time to collisions, and to design if its agent has a better uh, safety awareness compared to the human drivers. This is what we use to qualify. I don't know if
I
this.
guess you will show some metrics in the coming slides, right?
Yeah, I would like to show maybe the
Okay.
time to collisions.
Yeah, I have the same questions.
Yeah,
Let
but
him.
but I what I really want to ask is like how can you integrate the level of human and AV interaction into the learning process, or you just you just mix the real world data with the simulation data? Is this?
Yeah, I just mix the real world data with simulation data. Yeah,
Okay,
this is.
so you don't somehow integrate the interactions into the learning process with, for example, like using a different reward function, right?
No, I don't use different reward
Okay, okay.
functions.
Yeah,
All
just to
yeah,
be clear. Yeah,
yeah.
yeah. Okay, go ahead. Thank you.
Okay. Yeah, next, we evaluate our agent with another dataset, which is engine sim dataset. And here we have two the same old velocity and the bumper to bumper gap. And we also, yeah, we add performance metrics, which indicate the safety, which is time to collision. And yeah, and time to collision, basically, it measures how far these two vehicles pairs will collide with each other if they keep their current distance, current speed. And we consider that TTC under 2 seconds is safety critical. And yeah, from the evaluations, we see that the real follower, which marked as green, and IDM follower marked as purples, shows a more aggressive, risky driving behaviors, which making the time to collisions sometimes smaller than 3 seconds, and the IDM followers sometimes also make the time to collisions smaller than 2 seconds, which is quite safety critical. And also our proposed agent is able to have the high time to collision across all the scenarios.
There are other metrics besides just TTC, right? I mean, it depends on
Yeah.
how jerky the driving is, so how much oscillation there is in the accelerations. Also, if you keep too much of if your TTC is too large, then other vehicles will come in the middle of your platoon. So,
Yes, but however, here we just consider maybe the car following behaviors. There's just two vehicle pairs, and I think we have two
so
measures.
you're just considering this pairwise then,
Yeah,
pairwise.
pairwise, and we also have the bumper to bumper gap, which we can identify whether the vehicle keep a suitable distance to the leading vehicles. And we can see this from the middle columns of the plot.
So your data set, the Italian data set, Napoli data set, that had 5 cars, but your evaluation just has one pair.
Yeah, they have 5 cars, but they have 4 pairs, right? And we use 4 pairs always. We use the 4 pairs and we extended it. Yes.
Because when you say platooning, they have some kind of effects that transfer. So the vehicle right at the end of the platoon will have to have more extreme reactions because of the delay in the reactions in the
Yeah.
like so there is a difference in the dynamics of like just 2 vehicles versus 5 vehicles.
Yeah.
But you're just considering a pair. Okay,
Yeah,
good.
and I think during the collections and in the paper, they said this during the collections, the vehicle in the where only considered to follow the leading, so
Okay,
the flying
the
vehicle
leading.
just leading. Yeah,
Oh,
and yeah.
sure. Go ahead.
Okay, so next, and we extend maybe our research to a more general driving scenarios, which we still want our agent to perform responsible and make reliable decisions. And we want our agent to have the anticipation capabilities to other road users. And we still also want our agent to maintain the normal driving objectives. And therefore, we have the normal driving objectives, and we have the one objective that we want to minimize the risk assigned to all the road users. And therefore, we propose hierarchical safe RL frameworks for these dual optimization problems with a Lagrange multiplier. And we can recall that the objective of the normal RL is to maximize the return, right? And now the new objective here is to not only to maximize the returns, we also want to minimize the cost or the risk assigned from the equal vehicle to other vehicles. Here is defined as dpi, and eta is a cost limit. Basically, it says that we want our agent to maximize the reward according to the normal driving objectives. We also want to control the cost limit assigned from the equal vehicle to other road users to minimize the risk to all road users. And this is our framework. We have the simulated environment, and we have the pedestrians, we have the cyclists, and we have other vehicles. And our IR agent will generate trajectories, and we generate trajectories, and we also have a trajectory prediction framework, which is used to predict the trajectory of other road users, other vehicles, and other vehicles. And we use a prediction network, which is recurrent neural network, and with a grid-based system, and then we can predict the trajectory of other road users. So why we use this? We want to calculate the risk assigned to other road users. For this, we have the collision probability. If we want to calculate the collision probabilities, if we execute the current applied trajectories from our ego and with the predict trajectories of others. And we can also compute the harm severities and according to the collision probabilities and the trajectories. And why we consider this as ethical reasoning? So we have this cost function defined to address these ethical considerations. First, we have the biased principles. The RI here is the risk to all the road users. The SR is the number of road users. And with these bias principles, we try to minimize the risk to all other road users. And you may think that this can be somehow biased because the agent might assign to bigger risk to maybe some individual road users. And therefore, we have these equality principles. And this principle basically try to fair distribute the risk across all the road users. And we have also the third principle, which is max-min principles. And we decouple the collision probabilities with harm, and we want to minimize the maxima harm assigned to all the road users. And with this cost function defined, we want to minimize this cost and try to make the risk distribution across all the road users more fair and ethically. As part of my, we already have the collision probability, and we want to have this anticipation capabilities. Therefore, we design and we use the LSTM-based networks for our agent, to let the agent to know the context, and because our input is the information about the surrounding vehicles. If we add the LSTM-based networks, the agent can indirectly predict the intention of other road users.
So do you define like this ethics? Because I mean, this could also just be seen as safety. Is it just like a utilitarian kind of ethics approach that you just want to do this min-max for the safety?
Can you repeat the questions? Sorry.
I mean, there are like, ethical is a very broad, like the word ethics is very broad, right? So you have to
Yeah.
define what kind of, ethical framework you are subscribing to, and why is this just not safety? Like, why is this not just a broader mapping of risk to safety? I mean, what makes it like ethical, right? I mean, it's your yeah. Maybe you can comment on that.
Yeah, I understand this question. So because in the simulations, we have the cyclist, right? We have the pedestrians, and ethical means that because we also have the harm severity defined. So if we crashes to a pedestrian or a cyclist, of course there is a bigger harm compared if we crash it to a vehicles. And we want to combine the collision probability with harm severities, and therefore we can protect the vulnerable road users. So this is how we just proceed these ethical considerations.
Okay, but you could just encode that as a higher cost for less protected humans. Is that right?
Yes, we could do that. Yeah, of course. And
Okay.
yeah, yeah. Yeah, this is what maybe we are currently working on, and I think with this we can more not only focus on the normal driving objective because I will discuss one more baselines in later, and we also want to maximize these problems, and we show the necessity of this.
Okay. Okay. Makes
Yeah, yeah,
sense.
okay.
Can I ask a
Um,
quick question?
yeah,
Can I ask a quick question about the
yeah,
empirical cost? So one is how do you define the harm severity? Do you have like a dictionary of
yeah,
how the severity is defined? And second question is, would you really trust the trajectory predictor to give you a reliable collision probability? Because typically these predictors are only trained with safe data. Like unsafe data are probably classified by the government. I'm just curious.
Yes, first question. Yes, we have a rule book here, and to define we also have empirical equations to define the harm severity. And second question, yeah, it's very tricky. So we predict and we train the model to perform, and the model and we also test and evaluate the model, and the error and the prediction error is quite low if we put the prediction horizon to maybe a shorter time horizon. And then we use maybe a median time horizon to predict the collision probability. And we use to up to 2 seconds. So within 2 seconds, and the prediction capability is quite okay. And yeah, of course, we cannot fully trust the prediction networks, and therefore we compute the just collision probabilities. We just don't just fully trust these predictions.
The reason why I was asking that question is the way you define risk is probability times or multiply the cost. And in general, like our day-to-day driving scenario, the collision probability is actually extremely low. Like I've been driving for more than 5 years. I have not had a single incident. So this probability, if we're talking about what's the probability of you driving to your institution and collide, it's probably, yeah, a lot of zero, you know.
Yeah, yeah,
And and I imagine that risk will be like very sensitive depending on
yeah,
both your
yeah.
prediction of the probability and the definition of the cost.
I understand your question now. So the prediction network will just output the possible future trajectories of other road users, and with maybe some means and variance of the predicted positions. And then we have our planned trajectories. And with these two trajectories and with a future predicted trajectory of other road users, we manually compute the collision probability because we have the variance from the predicted trajectories, and we compute the collision probabilities with these two trajectories, and not just one trajectory and with one cluster of trajectory. And then we have the collision probabilities. And yeah, and we don't predict the collision probability, and we predict the future trajectory. Then from the future trajectory, we just compute the collision probability. I don't know if this is your question.
Okay. Yeah, it's
Yeah.
clear to me.
Okay. Good.
But in
Uh,
your data set, you don't have any collisions, right? Or near collisions.
you mean
You just have good
for
driving data.
yeah, for driving data, but we don't predict the collision probability. We just predict the future trajectory of other road users,
I see.
and with
Okay.
variance, and then we compute the collision probabilities with our planned trajectory.
Okay.
Yeah. And then we have during the training, and we observe that the cost, and as you already said, the cost the cost is very sparse. At most of the time, it is near zero, and it's very very small. And therefore, we use prioritize experience replay to prioritize more the high cost experience to let the agent to learn more meaningful decisions. And we define two different driving modes for the ethical AR agent we named. And there is an ethical mode, which use the cost function defined here with three components. And there is also a selfish mode, which is just trying to minimize the risk to its assigned to its ego. And for the training, so we have our ethical AR agent with LSTM networks and dynamic PRs. And then we have some baselines. First, we remove the PRs to show why the PR is necessary for training. And then we remove the LSTM and to show why the LSTM is necessary for the anticipation capabilities. And here we incorporate the cost function directly into the reward function and making the dual optimization problem into a single optimization problem. And this can be, this probably is your previous question. And this is the training results. From the top left figure is the average reward return trained during the training. And we can see all these agents is able to achieve the same level of training and indicate that all these agents is able to maintain the normal driving objectives we define in the reward function. However, when we see the left and top right figure, which is cost values, only the ethical AR agent is able to control the cost limit within the cost limit, which here is used as 1. And to give maybe a more in detail understanding how this training looks like, we also plot the progress of the Lagrange multiplier. And we can see from the blue line here, the ethical AR, the Lagrange multiplier increase to a certain level, then it just converts to that level, meaning that the Lagrange multiplier controls the trade-off between the cost and the reward and maintain to that level. And for the ethical AR without PRs, and the agent, you can see the Lagrange multiplier is near 0, meaning that agent is not able to sense the cost at all. So the Lagrange multiplier doesn't work at all. And therefore, why this PR is important, is necessary for this training. Then we have the SAC lark, which we just remove the LCM networks. And we can see that this the Lagrange multiplier for this agent just all the time increasing, indicate that this agent is able to sense the cost, but due to the absence of the anticipation capabilities, it is failed to control the cost limit within the cost limit. Okay, then we move to the cost constraints, constraint identifications. And we define a matrix, we call it compliance, which is a percentage of steps which the cost is remain below the cost limit. And we have the overall compliance, which is the compliance over during the whole evaluation episode. And we have a safety critical compliance is when the cost is bigger than 0.2 during the evaluations. So this shows the compliance results. And we have different level of cost limit range from 0.1 to 2. And we have two different modes. And the first row is ethical mode, and second row is selfish mode. And from this figure, we can see that the ethical AR is able to achieve the highest compliance, particularly in the suitable range, from 0.6 to 1. And SACR and the agent without PRs is able to, it fails to learn and the LSTM SAC agent, which we combine the cost function with reward function, just fails to learn anything to control the cost limit, because this is because that the cost and during the training is very sparse, and compared to the reward function, and it's very constant, and it cannot learn anything to minimize the risk at all. And next, we have the risk evaluations, and we define two different risks. The first row is the ego risk, which is the risk assigned to the ego vehicle. Then we have the other risk, which is the risk assigned to the maximum risk assigned to all the root users. So we can see from this figure that the proposed agent is able to control the risk, either from the ego risk and to also for the other risks. And there is also one maybe very interesting point, and we observed that the ethical AR with ethical mode shows a less ego risk. This meaning that if you perform ethically for all the root users, it in turn also minimize the risk assigned to your ego. And here is maybe some examples from Waymo dataset we tested. And it's our ego vehicle marked as green is trying to make a left turn, and other vehicle marked as red also want to make a left turn. So in the common courtesy that our ego vehicle in the right have the right to drive first. But it's not always the case, right? And for the standard agent, which is LSTM SAC, also the SAC lark and ethical AR without PRs, the agent tends to just drive and make the left turns. And you can see when the T is equal to 4 seconds, and our ego vehicle tends to drive to make a left turn, and making the time to collision between our ego vehicle to other vehicle very low, and range from 0.4 to 0.8. And although there is no collision occurs, this is still very risky and unethical, we considered. And for the ethical AR agent we proposed, and it performs, it has the anticipation capabilities, and it just wait until the red vehicles finish the left turn, then it just to resume to further drive. Okay, then we have the normal driving capabilities. We evaluate the comfort. We have the accelerations. We have the jerks. And for accelerations, we consider also for jerks, we consider smaller than 1 is comfort. And from the figure, we see that only the ethical AR in the selfish mode shows a slightly discomfort behaviors, and all the other vehicles, all the other agents is able to perform a very comfort driving styles, which also converge with the reward results we showed before. And all the agent is able to maintain the normal driving objectives. Okay, so the next contribution, which is simultaneous
Excuse
transfer.
me.
Yeah.
So may I have a couple of questions about what you present in the so first of all, now I think you apply this method to the T-junction scenario that you show in slide 16, right? Can you go back one slide?
What?
Did you apply the technique that you present here to this scenario, the T-junction scenario?
You mean this scenario?
Yeah.
Yes. Yes.
Okay. So do you have for example, like a video demonstration for it? Because it's hard to visualize what is going from on those pictures.
Okay, so from the left, the time is from t equals 0 seconds to t equals to 5 seconds.
Okay.
It's column wise, so from left to right is the time horizon. Sorry, I didn't expand this. From 0 left to right, is time horizon, and for the row-wise, it's 4 different agents.
Okay, so can you clarify what does it mean by, I know ego vehicles is the
Yeah,
one that you control, right? So what
yeah,
does it mean by relevant vehicles and other vehicles? They are own
and
human-driven vehicles, right?
yeah, it's a relevant vehicle is here, and we define the relevant vehicle in these scenarios because here, if we are making the left turn, and there is also a left turner in our left, and this vehicle will interact with our vehicle when we make the left turn, and which is most relevant when we drive in these scenarios, and the other vehicle just the background vehicles.
Okay, so so for this particular scenario, I
Yeah,
mean, basically like if you have no signal at all, no, for example, no stop sign, no yield sign, then the
yeah,
ego vehicles may need to determine which pair of vehicles that they can cross in between, right? So in that sense, the relevant vehicles is not well defined in priority, in prior, sorry. So that means if you have three vehicles here, I mean, it's not clear for the ego vehicles which pairs of vehicles, which pair of human-driven vehicles, the ego vehicles may cross in between, may cut in.
yeah.
So how can you define that pair of vehicles?
It's just for visualization. It's not used in the information.
Yeah, we use the information and the input for our agents is the closest 8 vehicles. So
It's
as
not like
input,
that.
Okay, okay.
It's
this
just
is
for
just for
Okay,
showing why
okay.
this
So that means in training, there's no difference between relevant vehicles and other
oh
vehicles.
in the training we have 8 closest vehicles we use as input.
So does it mean like you only consider the closest vehicles to the ego?
8 closest vehicle from our current lines and to the next 2 lines.
Okay,
I have
okay.
I have another question here. So how do you calculate TTC?
And this the 2-dimensional TTT we calculated.
When you say that, what do you mean?
We have X and Y, and we have 2 directions. We calculate the TTC according to the X and Y coordinates.
So you assume that this vehicle is like a point mass? Like, what do do you get what I'm saying? Like,
Yeah,
are you calc
it's a point mass models defined in the simulations, and we use this to compute the time to collision. Yes.
Okay, so this time to collision is also kind of a flawed metric because it doesn't really take into account the like a bicycle model or any kind of dynamic model of the vehicle. It doesn't take into account, the like it doesn't project forward what the vehicle will do or how if it maintains like a constant turn rate and velocity, it will go in a specific direction. Like this TTC calculation, like why like it doesn't actually measure the it is it's not a great proxy for if you're actually going to hit this other car, right? Like it's only accurate in the extremes of cases. Is that not true?
Yeah, that's true. That's why we just use this TTC to validations and to show some kind of safety critical situations. And we don't use this for training, and we don't use this for modeling. And this is just for to show why this and to show these critical situations. And this is just for visualizations and for evaluations.
Okay.
Yeah, we don't use this
Okay.
TTC.
May I have another questions? So you trained this reinforcement learning policy using a simulator, right? I'm just curious, how do you build that simulator? Did you use a existing simulator or you build another?
Yeah, we use MetaDrive simulations. And
Mhm.
we import the real world data set. We use Waymo and NewPly, and we
Mhm.
import all the trajectories into MetaDrive, and then we train our agents within this. I mean, it's real world driving scenarios we can see.
Okay, okay, okay. I see. Yeah, thank you.
Yeah. Okay. May I continue now?
Hmm?
Yeah, go ahead.
I have it.
Okay. Okay, so next we move to the sim-to-real transfer. And before we dive into the sim-to-real transfer, and we conduct a large-scale survey for the small-scale car platforms. And first of all, why we do this? Because the small-scale cars has a low cost. I think you all knows, and it's safer to do the experiments. And it has a more wider range across, for example, for the educational purpose or for the research purpose. And it can also bridge from the simulations to the small scale platforms and also from the small scale to a full scale testings. And for the survey, we covered almost 20 plus platforms, including one F110s, which is one of the most important platforms, of course. And we categorize the hardware and software, and we covers also the different driving tasks with lane keeping, racing, and cooperative drivings. And we test and we conduct and we served a different method we can use for lane keeping for different driving tasks and propose some possible hardware designed for the users if they want to assemble their own platforms. And then we move to the sim-to-real transfer. And we propose to use a so-called modular system to mitigate the sim-to-real gap. And first we have the perception module, which produce the informations necessary for driving. And then we have the control module, which we use reinforced learning to use the input from the perception module and to control the vehicle. And with this system, we perform the car following, lane keeping, and overtaking behavior. And across the simulation environment, we have the gazebo, and we have lucky town environment, and we also have the real world testing. And yeah, for the perceptions, we use a pipeline from Dakiton. And first, we have the camera image. We do some initial clustering and cluster the colors of different line components. Then we have the Canon edge detections together with the color thresholding. And then we have used the Hawk transfer to compute the line components from the lanes, lane components from the lines. Then we project the lanes to the word frame. Then we use parametric histogram filters to estimate the lateral and orientation deviations. And to the right line center, which we will use later for the control. And for the control, we have the LSTM-based RL agent. And the observation includes the lateral and orientation deviation we get from the perception model. And we have the velocity, and we have the heading error, and we have the cross-track error, and also one binary flag, which indicates if there is a vehicle in front. Then we have the actions, which is the speed and the steering for the vehicle. And we define the reward function, and which is first component is a lane keeping reward. We want our agent to drive within the lanes, right lane center. And there is also a so-called velocity bonus. And we want our agent to drive with the desired speed, if necessary, making overtaking maneuvers. And there is also a heading penalty, and we want our agent to drive with the line directions. And then we do some iterations, and we evaluate the agent in the simulation. First, with for the line keeping capabilities, we have the comparisons with PID controllers, also with some human baselines. And then we evaluate also the capabilities for the overtaking maneuvers. Then we evaluate also in the real world for line keeping and overtaking. And first, for the evaluation in the simulation for line keeping, we define some performance metrics. First of all, is the survival time. It's basically how long your agent is able to drive within the simulations without crash or without driving off the road. And we have the travel distance, we have the lateral deviation, orientation deviation, and the major infractions. And we have the baseline. First is the PID controller, which directly uses information from the simulation without any procession modules. And this is not available for the R agent. Then we have human baselines. And we test and we let the human players to play line keeping in the simulations. Then we took the best performance and for comparisons with with PID controllers and R agent. And for the R agent, we have two different modes. We have the fast mode and we have the slow mode. And the difference is the desired speed for these two modes is different. Set it. So we evaluate our agent into 5 different maps, um, compared with different baselines. And from the trajectory, we already can see that the RL agent shows a more smooth trajectories compared to the human baselines. And also the PID baselines also show a very smooth trajectories. And to give a more detailed comparisons, we design a matrix, we call it final score, which is the sum of time traveled and distance traveled, minus the lateral and orientation deviation, and also minus the major infractions. So this table summarizes the results we during the evaluations. Yeah,
So
from the
in this case, your vehicles are moving at what, like 2 or 3 meters per second, or like very like slowly, or
yeah, it's quite slow,
okay,
and there is no, I think, you can see the survival time for this vehicle is 60 meters, 60
60 seconds.
seconds, and the travel time is around, I think there is travel time defined. It's basically 0.6 to 0.8 meter per second.
Okay, okay. So it's
Yeah,
pretty slow then.
yeah, it's slow. It's slow.
So how,
It's
how
for the big scale, small scale vehicles. It's not for the full size vehicles.
so
So
how would your learning scale up, or I mean, or not scale up, but how well would it work as you increase the speed? Like say if you
um,
go at like I don't know, 6 to 8 meters per second, then
Okay, so in the simulations, it's not possible to drive that fast for that vehicle. So we
hmm.
didn't test with the higher speed. So the fastest the vehicle can go is 1 meter per second.
Okay, okay.
Yeah, yeah. Okay, so may I continue
Yeah, yeah,
now?
yeah,
Okay. Um, okay, for the overtaking, and we add a more one more performance metrics, which is overtaking success rate, and we test within 3 different maps. And the agent is able to achieve over 90% of overtaking success rate. And also the lateral and orientation deviations remains same level compared to the line keeping, and indicates that our agent is able to perform safe overtaking maneuvers when there is a vehicle driving in front. And after the overtaking maneuvers, the agent is able to drive back and to resume the line keeping behaviors. And yeah, for the real world line keeping evaluations, we have and we add 2 more baselines. First is CNN-RL, which we use the CNN to predict the lateral and orientation deviations. Um, just replace the precession model we defined before. Then we have the end-to-end RL agent. Then we trained the RL agent in an end-to-end way. And this is the trajectory, collector trajectory for the baselines. And we test with 5 different tracks. And we show that the proposed agent is able to output more smooth turning and turning trajectories, and it perform constant across 5 different tracks. And we also test the agent in the real world for overtaking. And from the videos, you can see that the agent is able to perform overtaking maneuvers when there is a slow vehicle driving in front. And after the overtake, the agent is able to just come back to the right line and resume for line keeping. And this is the trajectory collected. And the red trajectory is a slower vehicle, and the blue trajectory is our ego vehicle. And the red circle blocked the area where the overtaking maneuver happened. And we also test our agent to overtake the static obstacles, showing that the agent is able to adapt different scenarios. Okay, so we move to the summary, and there is 3 different contributions. First, we design a framework that can output a suitable agent that performs better or suitable for human-machine interaction scenarios. And we train an agent that has ethical awareness and is able to minimize risk or the fair distributed risk across all the road users. And then we have the sim-to-real transfer capability of the platforms we can use to mitigate the sim-to-real gap. However, there are still some limitations. And all my work is focused on single agent, and the multi-agent uncertainty still remains a challenge and should be addressed maybe in the future. And also, although we use a modular system to tackle the externalities, the black box nature of RL still limit the externalities. And this is what we would like to do, also work on in the future. And we test our agents in the small scale platforms. We also want to test with more realistic full scale vehicle testings. And also for the ethical reasonings, and we have the risk probabilities, which is quite simplified. And we also want to have a more realistic collision probability or risk probabilities computations. And yeah, moving to the future plans, and I would like to work on maybe for the responsible autonomous driving, including explainabilities and trustworthiness. And there's few directions I would like to go. First is the expandable and the multimodal RL. And we can incorporate the large language model for the expandable behaviors. And then we use a vision language model for a more rich multimodal perceptions. And also for the ethical considerations, we also would like to have long-term social considerations for our agent. And we also need our agent to know the context when it drives and to make the trade-off more suitable in a very dynamic traffic environment. And we also want to leverage the uncertainty modelings and to transfer the agent into a more realistic platforms. Also, we want to establish systematic benchmarks, not only for safety and also for explainability and ethical performance in the whole autonomous driving system. Okay, so this is all my presentation, and thank you all for your attention. I'm very looking forward for your questions and maybe some discussions. Thank you.
Well, thanks a lot, Dianzhao.
Yeah, thank you for the opportunity.
As you can see, people are very interested in so many of the aspects with so many questions. So,
Yeah,
and
I'm
any
correct. Yeah.